Abhijeet Ghosh in 7th grade in device modification. Drowsiness and distractedness are two of the main causes of accidents, injuries, and deaths in cars. In 2018, according to the NHTSA and NSC, more than 470,000 injuries and 4,400 deaths were caused by these two factors alone. Traditional sensor-based technologies, such as automatic braking and lane assist, don't focus on the driver, they focus on the environment. Many states have tried to mitigate at least texting while driving by making this illegal, but this has had minimum impact because it is very hard to change drivers' behaviors and enforce this. Artificial intelligence has been advancing at a very fast pace, and the advent of small single-board computers, such as the Raspberry Pi, have made it very affordable to use artificial intelligence on the edge or locally. I decided to use artificial intelligence, a Raspberry Pi, and some cameras to detect drowsiness and distractedness in a car view. The heart of my device is a Raspberry Pi. It runs Raspbian, Debian, Linux, and it runs all the programs which are written in the Python 3. It is connected to a front view camera and a side view camera, which are used for drowsiness and distractedness detection respectively. It is also connected to a touchscreen display with speakers for audio and visual alerts. Finally, it is connected to 4 lighted buttons for controlling the audio alerts. The lights come on if the specific alert is enabled. First, the device will take an image from both cameras and resize it to the correct size. Next, it will crop the face from the front image. To detect the drowsiness, it will first find the shape of the eyes, and then if the eyes are too closed for too long, it will sound an alarm of drowsiness. Blinks are detected in a similar way, except without the time limit. If the number of blinks per minute is too low compared to a threshold, also another alarm will be sounded. In emotion detection, the cropped face is fed through an emotion detector, which will play music if angry or sad. In distractedness, a side view image is resized and sent through a distractedness detector, which will sound an alarm if the distractions are detected, and this will repeat many times a second. Now, let me explain you how my device works in detail. First, in boot up, the cameras are initialized, the libraries and the AI models are loaded. Then, the front view camera is resized to 224 320 by 240, and the side view camera is resized to 224 by 224. After that, the front view camera is fed through DLib hog frontal face detector. This crops and finds the face in the whole image. This step is being done so that the future AIs, such as the landmark detector and emotion detector, do not have to check the whole image, and they can be optimized and just check the face. How hog frontal face detector works is that it will divide the whole image into a grid of blocks of pixels. Then, in each block of pixels, the gradient direction, which is light to dark, is found. Then these gradients are turned 90 degrees and plotted onto a map. In this map, the edges will be exposed as gradients turned by 90 degrees show the edges. If the edges match a circular pattern, the AI will be able to see this pattern and detect that that is a face, and therefore crop it to that part of the image only. Next, this is fed into the DLib landmark detector, which will find various points or landmarks on the face, such as the jawline, the nose, the lips, and the eyes. After the points of the face are found, the EAR or the eye aspect ratio will be calculated. This is the ratio between the average height to the width of the eye. The height is calculated by the average Euclidean distance from between this point and this point divided by this point, or the width. The Euclidean distance is just the hypotenuse of the 2 points if they were the vertices of a right angle triangle. Once the EAR has been found, we can determine whether if the EAR is too low, that means their eyes are closed or partially closed. If this occurs for 2/3 of a second, the alert will be sounded in drowsiness. Now, let me show you my device in action. As you can see, if I am driving and I start to get tired, it sounds an alert to keep me awake. Here, you can see now the device is running in a car environment. A byproduct of the closed eyes detection is that it can detect texting.
Focus on the road.
This is the primary method for drowsiness detection, but a secondary method is slow blinking detection. Studies show that a 50 to 70% of the normal blink rate can signify loss of attentiveness, fatigue, or drowsiness. Blinks are detected in a similar way to drowsiness, except to closed eyes, except for a shorter time of only 1/5 of a second versus 2/3 of a second. If the blink rate, which is calculated over 1 minute, is lower than 65% of a threshold blink rate, an alert will be sounded. Now let me show you blink detection in action. This is individual blink detection, which is used to calculate the blink rate. Here, individual blink detection is happening inside a car environment. Some of the main driver distractions include drinking, texting, talking on the phone, and reaching behind. My device can detect these, so the driver is focused on the road and not distracted using a trained AI model. To train this model, I downloaded 2,000 images for each type of distractedness and 2,000 images of safe driving from a database called Kaggle, who is used in AI and data scientists. Then I trained the dense layers of a convolutional neural network called VGG16. A convolutional neural network has 2 layers, the convolutional layers, which extract features out of the image, and the dense layers, which give the final result and find patterns in these features. The final result will be one of the types of distraction or safe driving. During the training process, the dataset was augmented by randomly cropping and distorting each training image into multiple different images. This is done so that the camera, the angle, and the camera position and the size of the car do not matter as much, and the AI can still be accurate. To detect the distractions, a side view image is taken and resized to 224x224. Next, the AI can detect the distractions from the whole car environment from the image. If any distractions are detected, an alarm is sounded until the distractions go away. As I said before, the AI was trained using distractions in the cars, so I cannot show you the distractedness detection in this room. However, I have recorded this video clip of distractedness detection in action during testing, as you can see now.
Focus on the road. 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 Focus on the road.
Additionally, my device can detect emotions so that the driver is focused on the road and not preoccupied with their emotions. The emotions that my device can detect are anger, sadness, happiness, neutral, and surprised. The AI that detects the emotions is trained similarly to the distractedness detection, except it uses MobileNet, which has less computational power but is faster than VGG16. To detect the emotions, the cropped face is resized to 48x48 and converted to grayscale, then fed into the emotion detector. If anger or sadness is detected, a set of happy music is played so that the driver is focused on the road and not preoccupied with their emotions. This is the flow chart of my program, which summarizes and depicts the device's logic. Drowsiness, distractedness, and emotion detection are all highlighted in this flowchart. I tested the drowsiness, distractedness, and individual blink detection aspects of my device. In each test, I used 2 cars, 2 drivers, and 2 seat positions per car. The test, I had the driver get into the correct car in the correct seat position and do the desired action while the device was running. I recorded this, and later I watched the recording and logged the number of correct alerts, missed alerts, and false positive alerts. The accuracy, which is calculated using both the false positives and the missed alerts, for drowsiness detection was 99%, for blinking detection was 96%, and for distractedness detection was 95%, which are all very high. I could not get numerical data on emotion detection as it is very hard to imitate certain emotions, such as anger and sadness. For example, when trying to imitate anger, my parents, first of all, thought their expressions were very funny and started laughing, and second of all, their expressions did not look anything like true anger. However, for happiness, neutral, and surprised, the emotion detector had a high accuracy. In this project, a device that can detect drowsiness and distractions was built using a low-cost, readily available parts and materials. It is also standalone and will work in any car with 12-volt outlet, which is nearly all. Based on the testing results, the device detected drowsiness and distractions in various environments, many different cars/vehicles, many drivers, and different seat positions with a high accuracy. I have concluded that this low-cost, standalone, AI-based device could prevent many car accidents, injuries, and deaths, and improved car road safety. Future work includes adding a low aperture or an IR night vision camera for nighttime, testing the device in different kinds of cars such as pickup trucks and semi-trucks, and fine-tuning the AI model to reduce false positives and increase the accuracy. In this project, I learned many types of new AI models and object detection algorithms, such as histogram-oriented gradients, or HOG, and D-lib landmark detector. Furthermore, I learned to augment the data set by cropping and randomly distorting the training images. Finally, I learned how to use Python multithreading, where multiple AI/functions are run at once so that the processing completes faster. The first time I trained my distractedness detection model, it had a low accuracy and could not detect the distractions well. In that time, I did not augment my training data. After augmenting and retraining the AI model and data, the AI had a much higher accuracy as it would work with the minute differences in the camera angle, car size, and camera position between the testing data which I collected and the training data. Thanks you all for listening.